Last time we were taking a look at section 3.2 called addition and subtraction of whole numbers, and we had gotten to the point where we were going to take a look at a definition of the phrase or the words less than. And so the definition that your book is going to give is saying that for any whole numbers A and B, A is less than B, and it's written A, we've got that symbol that's opening towards the B, less than B, if and only if there exists a natural number K such that A plus K equals B. Okay? So you guys know this feels like an awkward definition partly because we just have this intuitive idea of what the phrase less than means. But being mathematically precise, the idea that 4, for instance, is less than 7 is simply true because we can add a number here to make these equal. And the number that we are adding is actually a natural number. What number would go in that blank? 3. And 3 is a natural number, right? It's a counting number. That's all this definition is saying. And it's saying it in terms of being able to add a number to the smaller value and equal the larger value. Now, if you think about it, there is a way to sort of fail the condition. Let's say, for instance, you, for some reason, because you weren't thinking very clearly, thought that 7 was less than 4. Right? Well, in order for that to be true, it would mean there has to be something to fill in this blank. What would we, what would we actually have to fill in this blank with to make these equal? -3. What's wrong with that? Yeah, the problem is that the -3 is not a natural number. And that's where it would actually fail to actually satisfy the conditions, is the natural number part of this. Okay, we are going to do the same kind of thing as this definition, but we're going to write the definition using subtraction right here instead of addition. Okay? So as we write our definition, this is example number 2, our definition is going to have almost exactly the same verbal language that the first one did. So we're going to start out the same way. We're going to say, for any whole numbers A and B, A is less than B, written A less than B. This is exactly the same thing. I'm just copying at this point, right? Copying the first definition. A is less than B. If and only if there exists a natural number K such that what? What has to be true to make this work using some kind of subtraction? Do you have an idea? Okay, I'm going to keep the A on the left, but this is what you wanted me to say if I write it in this order, right? Yeah. Yeah. So instead of having the K added to the left-hand side, I'm going to have the K subtracted on the right-hand side. That's all this is asking us to do, is saying that it's equal, there is an equivalent statement that says that we could do it this way. And if you take a look and think about it with the language we used before, of course we have this working. We would have 4, for instance, less than 7, and this makes sense, because if I tried to set them equal, I would be able to fill in this blank with a natural number, and it would work. And the same natural number, of course, works. I mean, it would still be the natural number 3. But that's the idea of it using subtraction instead of using addition. It's not bad, right? Just a different way of thinking about it. All right. Moving in a little bit different direction, the next thing we're going to do is we're going to talk about some whole number properties. And specifically, these are properties of addition. There's several whole number properties. We're going to go through them. Some of them are very familiar to you. One of them is probably not. And the one that probably is not very familiar to you is the very first one. And it's the one that causes people the most conceptual difficulty. So let's start there. If A and B are whole numbers, then A plus B is a whole number. And this is called the closure property. Okay? So this is not true for every set of numbers. Whole numbers are special to have this property. This is the idea that if I take two whole numbers, so imagine this room is filled with whole numbers. They're floating around in the sky. Maybe they're on little note cards hanging down from the sky. You guys have been in teacher's classroom when they put stuff in the sky, hanging down right before. Okay, so imagine they're all floating around in the air. So we've got numbers like 5 and 432 and 6,298. They're all floating around in here, every single whole number, and there's infinitely many. So we're running out of space. We might feel a little claustrophobic, right? You guys are having no fun today at all. Have some fun. Come on. All right, so they're all floating around in here. And we've got a door right there that's holding them in. They're holding them in here with us. Now, outside in the hall, there's other numbers. Give me an example of something that's not a whole number. 1/2. 1/2 is outside the room. What else? 1/3 outside the room. So the fractions are out there. Give me something that's not a fraction. What's that? 1.2. So decimals. Yeah, decimals are going to be outside the room as well. Something else. Pi. That's a different kind of number. Those are irrational numbers. So pi and square root of 2 and those kinds of numbers, they're outside the hall. There's one more here that I want us to hit. There you go. Negative numbers are outside the hall. And 0 to boot, actually, is in the room because it's a whole number. So 0. Okay, so let's take, for example, the fractions. So the numbers like 1/2 and 1/3 that you guys were talking about, okay? So let's take two fractions, and I'm going to be a little bit picky about what fractions I'm taking because I want to give you an example that shows you how this messes up. So let's say, for instance, I have the fractions 1/3 and 2/3, okay? I take the fractions 1/3 and I have the fraction 2/3, and I add them together. What happens? I get the value 1. And if all I have floating around in here are the traditional fractions, the way we think about fractions as being, a smaller number on top, lower number on bottom, that kind of stuff. You could even do mixed numbers if you want in that kind of a description, but they don't have like 0 remainders, right? Like I actually have a fractional part of something left over. If I'm adding the 2/3 and the 1/3 together, I get a whole number, right? But the whole numbers aren't in the room. Not right now. It's just the fractions, correct? Which would mean I'd have to open the door to find the solution, which means the set's not closed. Closed means I have all of the values I need right here. We can all be good with the values that are here. So that's one way you can fail. You can actually have a group of numbers that just doesn't work with the particular operation of addition. You could also have an operation that doesn't work with the group of numbers. Now we're going to come back to this one in a minute because we're going to look at subtraction. But let's say we do this with subtraction now instead of addition. Whole numbers are in the room. Okay, so 0, 1, 2, 3, counting numbers, all that good stuff, plus 0. Those are the only things in the room now. The door's closed. All the rationals and irrational fractions, irrationals, those kinds of things are all outside. So what happens if I take two whole numbers and I subtract them? 5 minus 3, what is that? 2, is that a whole number? Fabulous. What if I do 3 minus 5?
Open the door.
I have to open the door because I might get a negative when I subtract, right? I have the ability to take two numbers with the subtraction operation where it does not hold that the door stays closed. So that would be an example of a set that's not closed under the operation of subtraction. So this idea that we have something, this closure property, is really an idea that's specific to two things. You have to know the set of numbers you're talking about and the operation that you're working with. The set of numbers here is whole numbers. The operation is addition. And we'll come back to subtraction in a little bit and talk about these. Okay, so that's the one that everybody gets confused about. So let's say, for instance, that I had even numbers. I mean, it doesn't have to be whole numbers. It doesn't have to be any of these specific numbers. It's just even numbers. When I add two even numbers together, do I get another even number? I do. So even numbers would be closed under addition. Okay? What if I have odd numbers? That is not going to work, is it? What happens when I add two odd numbers together? I get an even number. And if the odd numbers are the only thing in the room, then I would have to open the door to find the even number answer, correct? Okay, so it really matters the set that you're working with of numbers and the operation that you're working with. That's closure. Commutative. I think you've probably seen and worked with commutative quite a bit. You probably use it all the time without even thinking about it. Commutative is the idea that the order that we do addition in doesn't matter with whole numbers. 5 plus 2 is the same as 2 plus 5. Again, that doesn't work for every operation. And we'll come back to that with subtraction in a minute. 2 more properties. Associative. Okay, so the associative property, what do you notice when you see the associative property that we didn't have with commutative? There's 2 things to notice. Parentheses. What else? A C. There's actually has to be 3 different numbers for this to make any sense. Associative property has very much to do with the word associate. So when you actually talk about when you associate or who you associate with, you're asking yourself, who do you group up with? Who do you hang out with? And that's what those parentheses are doing. They're grouping things together. Okay? So that's where the associative, sort of the word for that is coming from. And what this is saying is that when I have addition of 3 values, it doesn't matter what I associate together. If I associate the A and the B and then add the C afterwards, or if I associate the B and the C and then add the A afterwards, it gives me the same result. And that's often very friendly if we had quite a few numbers to add together, and some of them add together to give me really nice values like 10 or 20, and others add together to give me awkward values like 17 or 26. Well, I want to have as many nice values as I can, and so I might regroup them to actually have them add together in a more convenient way. Identity. I want you to make one note here, because this happens every time we get to a test where I ask a question about identities. This is the additive identity. It should already sort of be, you should be aware of it because the word's addition up here. But very, very specifically, this is the additive identity. Now, technically, these are all additive properties, so it's the additive property of commutativity, right? It's the additive property of associativity and all that good stuff. But it really, really matters here because the additive identity is something different than the multiplicative identity. They're not the same thing. So when we're talking about this is the identity, we really need to specify which identity we're talking about because they're different numbers. Okay? So the additive identity is simply a number that when we add it to something, it doesn't change the something that we added it to. It's special. It's the number 0. 0 is the additive identity. So the additive identity has this ability to be added to something and not change something else, change the thing you're adding it to. Any questions on those before we try an example with this? Okay. There are 4 problems listed here. I'm going to give you 1 minute to actually fill in what you think the answer is. If you're using pencil, it's probably a good idea. You're trying to figure out which of the 4 properties above fits in which blank. And it's not necessarily that each one of them is exactly one answer, okay? In fact, it's not. You can use a value. You can use the answer more than once or an answer not at all. So your goal is to figure out which property is being used in which example. If you do get finished, go ahead and put your pencil down just so I know you're done. Okay, is that everyone? Okay. Jamie, what did you put for the first one? What do you think that one was? Did anyone else get commutative on that one? Yeah, good. That's the commutative property. Very good. Commutative is a hard word to spell for some people. Maybe if you've got some spelling difficulties, you might spell that one wrong. It is not communicative or commutative. Commutative. I get lots of interesting spellings on this one. Commutative. Cassidy, what did you get for the second one? What did you think that one was?
The identity property.
Right. Specifically, which identity property? The additive one, right? We're working with additive, and we only have that one at the moment, but we'll get in the habit of it now. Did everybody else get that additive identity on that one? What's the giveaway? 0. You see a 0 in it, right? It is. It's a giveaway. Okay, C and D both have some parentheses involved. So when you're looking at C and D, you might be tempted to sort of do something with associative because of those parentheses, but you do need to be a little bit careful, right? Okay, Abby, what did you get for C?
I said community and associative.
Okay, so you put both of them. So let's just, out of curiosity, who did put commutative? Okay, who put associative? Okay, we have a split decision. So let's take a look at it. When we compare the left-hand side and the right-hand side, what's different? Okay, so this is what Amanda's seeing is different right here. Is that what everybody sees? Is there anything else that's different? Not on this one, actually. It's just those values. And what's different about them? They're switched. The order switches, right? So which of the properties talks about order switching of the values we add? Yeah, this one is commutative. Don't let those parentheses throw you. Really look at what's different from one side of the equation to the other side. Okay, how about D? Tiara, what'd you get on D? Associative? Did anybody else get associative? Yeah. If you're looking at this one, because we did this on part C, so let's be careful on this one as well. What's different on D from the left side to the right side? The what? The placement of the parentheses. So here the placement of the parentheses is around the 5 and the 3, and here it's around the 3 and the 2, right? That's what makes it and the other thing to notice that's the same is that the order of the numbers doesn't change, right? 532, 532. So it's not commutative because the order of the numbers didn't change also for that. So this one is associative. Good job, guys. Okay. The next thing we're going to do is we're going to actually take a look at some strategies for actually doing addition. Some of these strategies you will see used in textbooks that are currently being used in the public schools nearby. You may have already even seen some of these used. You don't have to like them. You do need to know what they are so that if you're asked to teach something from curriculum that uses them, you can do that. That's the kicker, okay? My daughter came home, my 10-year-old, from school the other day, and she's working with factoring. Okay, it's not this topic. She's working with factoring, and her teacher showed her how to factor in 2 ways, and her teacher actually made the comment, there's also a 3rd way to factor, but I'm not going to show it to you because I don't like it. And it's like, oh, but what if that really worked for some kid in there? What if that was the one that made sense? And I don't know what the method was because, Abby didn't show it to me. But it's one of those things that you have to be really careful of. So we want to make sure that you're aware of these strategies and you know how to use them. Here's the first one, and this is one that's, this is an oldie but a goodie. This is the counting on strategy, and there's a counting on addition and a counting on subtraction, so that's a little confusing. But the counting on addition says you start with one value and you count up to the additional amount of the other value. So an example would be something like 4 plus 3, okay? And so usually what you see kids do is something like this, 4, 5, 6, 7. They count up, and they usually do it with their hands. Their hand actually has the number 3 on it when they're done, so they know when they stopped, and they know the number they said when they stopped is actually their answer. That's just called counting on strategy, okay? And it doesn't matter, again, whether you start with 4 and go 5, 6, 7, up 3, or whether you start with 3, 4, 5, 6, 7, and you count up 4, right? So typically what we would say is that if you're working with a kid on this, is start with the bigger one, so that they have to have fewer hands up, fewer fingers up kind of thing. This is counting on strategy. Have you guys seen and used that one before? It's a pretty common one. The next one, less common, called doubles. Personally, this is not my favorite, but for some kids, it really is very helpful. Doubles is the idea that before we sort of teach kids the idea of adding, like the ones table, like 3 plus 1, 4 plus 1, 5 plus 1, 6 plus 1. We don't start there. Usually if you're working with doubles, you start with adding only values that are doubles. That is, you learn what is 1 plus 1, what is 2 plus 2, what is 3 plus 3, what is 4 plus 4, what is 5 plus... You only learn the double values, okay? So here's how this works. If I know that 3 plus 3 is 6, and I'm asked to find 3 plus 4, instead of thinking of 3 plus 4 and doing something with counting like we did in the last example, we look at the 4 and we say, well, 4 is almost like a 3. I can break the 4 apart into the 3 and the 1 that you see at the very end there. So the 4 gets broken apart into a 3 and a 1. And I can use the fact that I know that 3 plus 3 is 6 to find that this is just 1 more than 6. This is 1 more than the double value because the 4 is 1 more than 3. That's why it works. Okay, it doesn't work for everything, right? This does not make sense to really use if I'm going to do 3 plus 5. But using 3 plus 4, because it's a near double, is where you would see this used. Has anyone seen this one used in the schools before? Both my children have brought it home from the public schools, so I know it's there. So you may see, it's strange, isn't it, Kaylee? It is strange. So you may see this one if you're teaching somewhere in the kindergarten, first grade ages, okay? All right, there's another one here. Making 10. I mentioned this one earlier. I actually am a big fan of this, and you probably use this without ever having realized that it's actually a method when you have done something in very practical, everyday kind of life. Like you went to the grocery store and you're trying to make sure that you have enough dollar bills to cover what's in the basket, that kind of thing. And you say, oh my goodness, well, this item was 35 cents and this item was 60 cents. That's about $1. And you kind of put them together in such a way that they made a whole value that was something nice. This is the idea here. So making 10 is the idea that we take some of the pieces that we have and we make 10 out of them. So if you take a look at 8 plus 6, obviously 8 plus 6 is not 10. But there is a number that I can add to 8 where I do get a 10. It's the number 2. So again, in this method, kids really learn what makes 10. They know that 8 plus 2 is 10, and 6 plus 4 is 10, and 7 plus 3 is 10, and 5 plus 5 is 10. And those are actually really good things to know, obviously, right? Just like knowing the doubles values are good things to know. But they very concretely know what numbers add together to give you 10. So when they see the 8 and the 6, they say, I'm just going to break the 6 apart into the part that makes up the 10. That's the 2 that I need. And what's left over, the 4 I don't. So you're breaking it into 2 pieces. And you do that so that when you get the 8 plus 2 here, you actually have the 10 that you memorized and knew from the get-go. And then you have the 4 more. We're going to see making 10 happen again in another lesson, actually. Okay, we have 2 more, I guess. Counting back, these are subtraction properties. So counting back is the idea of starting with a higher value and counting back to the lower value. So these are our subtraction on this slide. Okay, we're looking at subtraction properties. So you're starting with, so let me give you an example. Let me do one. Let's say that we're doing 7 minus 2. Okay, so you can do this in one of 2 ways. It depends on how the number is you're subtracting from. So this one, actually, the way it's exactly stated, it says start with the higher value and count back to the lower value. So you go 7, 6, 5, 4, 3, 2, and the answer is what's on your hand, 5. So you actually count from the larger number all the way back to the smaller number, and however many you've counted backwards is that value. And if you think about it in terms maybe like of a number line model, we talked about this a little bit last time, what you're saying that you're starting at 7 and you're counting back to where you ended up if you went all the way to 2, and the question is, what value did you pass through? How many numbers did you cross over? That's the counting backwards process or strategy. And then counting on kind of works sort of the opposite way. With counting on, you still subtraction, so this is still 7 minus 2. But what you do is you start with the lower number instead of starting with a higher number. So you start with the 2, and you count up until you stop at the higher number you have. So 2, and then you have 3, 4, 5, 6, 7, and the answer is still the answer on your hand. So instead of starting at the top and counting back, which is sometimes difficult for kids to do, you don't memorize your numbers backwards, usually. That's not how it starts with, right? Think about little Johnny, who's 4 years old. He can count forward really well, but counting backwards is trickier. Then the second process is actually a little bit more intuitive. You start with the lower number, count up. Any questions on these? Okay, so just to clarify, did I say you have to love any of these? No, you don't have to, okay? But you do need to be aware of them and know how to use them if you encounter them. All right, so let's take a look then at subtraction. Subtraction of whole numbers. For any whole number, A and B, where A is greater than or equal to B, A minus b is the unique whole number c such that b plus c equals a. And again, this is a definition that makes more sense if I put some numbers in there, okay? So let's say, for instance, and you have to follow the conditions as they appear. The first condition is that you have to pick a number a that's bigger than or equal to b. So pick me one. 6. And what is 6 greater than or equal to? 4. Fantastic. So we've got 6 and 4. Then what this is saying is that the 6 minus the 4 will be a unique whole number. And it will be a unique whole number such that when I add the 4, like the answer here, I'll put a question mark. When I add the 4 to that answer, I get back to the value a, which I started with, which is the 6. So in other words, why is 6 minus 4 2? Well, 6 minus 4 is 2 because 4 plus 2 equals 6. And this is exactly how kids learn to subtract. They learn addition first, right? And kids learn how to add first. It's a lot easier to sort of combine things together and count what's there. And the next thing they do when they're learning subtraction tables, things like that, is they do things like this where they say, what is 6 minus 4? And if they aren't able to do that sort of quickly, one of the questions they might ask is, well, what do I have to add to 4 to get to 6? Because then I turn it into an addition problem, and I know my addition tables. I know that there's an addition process that I worked through before that says 4 plus 2 is 6. Oh, so the answer must be 2, because that's the missing piece in what's going on. The other thing that this sort of description does is it lends itself to the idea that an equal sign does not mean and the answer is. How many of you learned equals as though it means and the answer is? I know some of you did because on papers, I don't think it was in my other class, I think it was in this class, a lot of you put lots of extra equal signs between things that really weren't equal. You actually meant and the next piece is, and the next step is, and the next step is. Well, that's not what equals means. Equals means both the sides are balanced, right? They're actually equal to one another. And so the fact that I don't have the answer and it's not, and it's on a side of that's not by itself is actually working our way towards what it looks like to actually do equations when you get into junior high, right? Because I've got this blank space right here that looks an awful lot like what we're going to put an X in when we get older. And so it has a natural pull into algebra. Okay, we're going to have, I think it's 4 models of subtraction. Yep, it is. First model of subtraction. This is the most well-known. If I asked you what subtraction was, some of them you would actually say it's takeaway. Okay, so this is the takeaway model of subtraction. This is only one of the 4, but this is the one people think of usually first. This is an example of the language used in the takeaway model. And then I'm going to show you an example of the visual that's used when we do this model. Takeaway. Abby had 24 rocks. Eli sneaked into her room and took 5 rocks. How many rocks does Abby have now? Abby and Eli are my kids, just in case you had forgotten. This is something he would do, so this is why the problem's created. All right, so visually, what this happens when you're working with the really young ones is that this has a very visual feel to it. So we're going to draw 24 rocks. I have 24 circles that I'm going to call rocks. Sound good? I have 24 rocks. And we have Eli come in, and he takes something without asking, because I'm sure nobody ever does that in your house, right? Of course not. It's just my house. Oops. And so we're going to take away 5 rocks, and you can take them away from wherever you like, but these rocks are no longer in the room. So when you're very first working with kids in a concrete sense, this visual imagery allows us to actually count up what's left over when we do the removal, right? So how many rocks do I have left when I remove these? Somebody said it. 19, right? 19 rocks. This subtraction problem was 24 minus 5, right? So I'm doing 24 minus 5, and that ends up equaling, I'll put in equals because that's actually true in this case, equals 19 rocks. All right, ready to take a look at another one? Elise needs to collect 10 leaves for a school project. Did anyone ever do leaf collections in school? Yep, okay. 10 leaves for a leaf collection at school. She and Temeskin go out and find 8 leaves. How many more leaves does Elise need? All right, so we're going to draw some leaves. I'm even going to change to green because that's how much fun I want to have right now. I'm going to have green leaves, okay? So we have, they're kind of circly leaves. You know, they don't really look like leaves. I'm not pretending they do. It says she needs 10 and she has how many? 8. There it is. 8 leaves. So I'm going to draw in the 8 leaves she has. And what I'm missing is I'm missing something in this case, right? It's not that she had 10 and she lost 2, or she had 10 and somebody took them away. She never had 10. That's just how many she needs. That's different than the first model, isn't it? It really is. That's a very different kind of subtraction. So, how do I draw it? Well, I draw the 8 that she has, and then I need to draw what's missing. So, I'm going to draw this. Let me see if I can get it drawn the way I want to. Oh yeah, that works. Look at that. Those are the ones that are missing. There's 10 placeholders, so to speak, and the 2 that are dotted in my picture are the 2 that are missing. This is how you draw a concrete model, a physical image of what it actually looks like for what's going on. The other thing that you can do is you can actually draw it in an equation form, and we talked about this when we talked about the definition of subtraction. She has 8 and she needs 10, and the question is, what is missing in that blank? And the answer is 2. So we have 2 leaves. And of course, the problem that we've been working at on this one, I didn't write it down, I should, is 10 minus 8. Make sense? All right. Next one, comparison. Madeline and Monique play basketball. Madeline scored 12 points and Monique scored 8 points. How many more points did Madeline score than Monique? All right, so in this picture, I'm going to draw my points as tally marks. That's how I'm going to choose to draw them. And so I'm going to have Madeline with 12 points. And I have Monique with how many? What was hers? 8, right? 8. So I'm going to draw this. Madeline's first. And Monique is second. And so Monique has 8 points. And I'm going to line them up with the first 8 points of Madeline. So what I'm noticing then is that these at the end don't have a matching pair. Correct? That's the answer to the question. That's the answer visually to how many Monique does not have that Madeline did. It's 4. So if we're trying to compare something, we want to have some kind of visual imagery of how to actually do that comparison. Okay, I have exactly 1 minute left according to my watch, and that clock is doing funny things. So let me show you the last model, and we'll stop. Akeem. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls and asks him where he is. He states that he's coming home, and he's driven 8 miles so far. How far is Akeem from home? So this is a measurement model. It's using values. We talked about this last time. Using values where partitioning it down makes sense. Like, can I talk about a half a mile? Yeah. Okay, so we're actually not counting objects, we're counting, in this case, a distance. So a number line model is a really good picture for what's going on here. So here's home over here. And some of you guys draw me really pretty pictures. Who drew the really, really pretty picture of Neverland and stuff on your test? Is there someone here today? Oh, somebody drew me a wonderful picture. It was so good. All right, the other one was the mall. So here's my mall, and it's really big. But I did not draw a good picture because I don't draw. And supposedly, what we're being told then is that this is 15 miles. And Akeem told his mom that he has done a return trip of how far? 8 miles. So visually, the question that we're asking for is, what is this length right here, right? That's the visual. This looks and feels a lot like missing add-in, doesn't it? What's missing? What piece has to go there to make up the 15? But it's done with a measurement sense instead, something that we're measuring a length of in this case instead of measuring or counting a value of. So the question ends up it started out as 15 minus 8. And of course we get the answer of 7 for that piece that's there, and it's 7 miles. Any questions on that one?